All right, hello. So in our last video, we went over the first challenge in the ROP Trainer demo that I created. And today, we're going to move on from basic buffer overflows and actually learn about the full ROP chaining attack. But let's start, like we did last time, with a bit more background. So just to recap what we did in the previous challenge, we did a basic exploit called ret2win, where we filled up this buffer with some padding, overrode the frame pointer stored on the stack, and then finally overwrote the return address with the address of the function we wanted to return to. And so we were able to call a function that isn't referenced anywhere in the original code. So yeah, pretty cool. Hopefully you guys were able to replicate that on your own. I hope my Docker image didn't break or anything. But yeah, let's go ahead and learn about some other exploits. So the history of buffer overflows is sort of like a cat and mouse game. If you've ever read the paper on smashing the stack, you'll know that there was sort of like a back and forth between new attacks being created and new defenses being created to counteract those attacks. But just going off of the basic buffer overflow that we've learned about at this point, we can use this technique to, one, redirect execution, as we just learned with that ret2win vulnerability. Two, we could override other local variables on the stack if we happen to have them defined after the buffer, or I guess it would be if they're defined before the buffer, then they can override those local values and potentially corrupt sensitive information. And more worryingly, we can even use this vulnerability to execute completely arbitrary code. And at a high level, how this would work, it's actually pretty simple. All we have to do is take whatever shell code that we want to execute, convert it to raw bytes, and then pass those raw bytes into the buffer. And then if we want to be able to run that code, all we have to do is overwrite the return address like we did last time, but instead of pointing at a different function, we point at the start of the buffer, or in this case, you can see we call that the address to the shellcode, because if we just jump to the start of the buffer, it's going to start reading the data that we wrote onto the stack as code and allow us to execute essentially whatever we want. Right, so we can start to see how these exploits can be very dangerous, but fortunately there is a pretty simple mitigation to this attack in particular, and that's called DEP, or Data Execution Prevention. And this is a measure implemented on, I think, all modern operating systems, and it's pretty simple. All it does is make a distinction between code and data, right? So this might come in the form of just like a flag in the page table entry for a page on the stack. And it just makes it so that user data input can't be executed directly anymore. So if we put in the address of the buffer where the return address should be, with DEP enabled, it won't actually run any of this code that we injected into it. So this will prevent that direct shellcode injection. And so what can we do instead? Well, the solution to this issue is the exploit we're going to talk about today, which is ROP chaining. And the idea behind this attack is if we're not allowed to execute the code that we're writing, what if we just use code that's already been written into the program, right? Like if there's this distinction between data and code, how about we just use the information that's already been defined as code? But I mean, that brings up another problem. How are we going to find this malicious code that we're trying to execute from just the benign binaries that we've been provided with? Well, fortunately, x86 actually gives us a very convenient solution and a mechanism through which we can enable this attack. And the key vulnerability we're going to exploit here is the fact that x86 assembly has variable length instructions. And what that just means is that different instructions might be different lengths. You can see here a return instruction is just a single byte, while this increment instruction is 2 bytes. And because each of these instructions is a different length, that means there's no fixed offset that we have to start reading these instructions from. And so depending on where we put the instruction pointer or where we have it start reading, the same block of bytes can be interpreted as completely different blocks of code. So we can see in this top block right here, well, we have this arbitrary block of bytes, and then the same block down here. And if we start reading here, it's increment EBP and then return. But then if we start reading here instead, it becomes increment RBP and then return. And if we keep extending our instruction pointer to start reading from here or here or here, what you'll see is that we'll get a bunch of different instructions all from this same binary. And so what this means, why this is so promising for us, is that in large code bases, for example, ones that are importing standard libraries like standard IO that come with a lot of code, this means that the binaries are large enough so that we can statistically find essentially any single instruction that we want to use. Okay, so, we can find any one instruction. I can find like an increment, I can find a return, but how is that actually useful? How are these little snippets going to help me construct that arbitrary malicious code that I was trying to execute before? Well, here's the idea, right? So this is the exploit called ROP chaining. And well, what does ROP stand for? Let's start there. It stands for return-oriented programming. And it's called that because the return instruction is key to the execution of this exploit. And so the idea behind how this works is that we're going to be chaining together a bunch of smaller gadgets, which are just small blocks of assembly code, consisting of usually one desired instruction followed by a return instruction. And you can think of this process like breaking a single larger program into a bunch of smaller programs. So let's say we have this arbitrary function. Let's turn this instead into, let's do function 1, then return, function 2, then return, and then function 3, and then return. And then maybe this picture will help as well. This is sort of a basic example of how it might go down. Let's say we wanted to execute some arbitrary shell code that executes this sequence of instructions, right? So we start with a pop EAX, then a pop EBX, then we move some registers, then we add them, then we pop them, and then we move another register. Now, it might be difficult to find this entire block of code by itself in memory. And when we're considering how we're trying to construct these malicious payloads, it becomes almost completely infeasible to just find, malicious code just sitting somewhere in the binaries already, right? And so the idea that we're doing here is instead of trying to find all of those instructions together, all we really need is each individual instruction followed by a return instruction. Because return will look for an address to go through from the stack, and by manipulating that address, once again, through that buffer overflow that we were using, we can tell it what gadget it needs to go to next, so we can continue executing on the next step of the chain. And so the application of this is that ROP essentially allows you to execute whatever code you want. And some common applications include, first, the one that we'll be working on, running a function with some privileged set of arguments. And this is a bit easier in x86 because functions in x86 are passed by register. Specifically, they're passed in the order RDI, RSI, RDX, etc. And what that means is that if you have a function that takes in arguments A, B, C, the way it's going to work is that those arguments are going to be loaded into those registers in that order, and then they'll be read from there, right? So you can imagine if you want to be able to set some arbitrary set of arguments before running a function, you could just be looking for these pop instructions and construct a ROP chain of all of those to get the values that you want popped into the correct registers. And a further application of this, which is actually going to be in the supplemental exercise that I've included in the demo, is that this can allow you to execute completely arbitrary syscalls, which can be particularly dangerous because it can be applied to things like privilege escalation or, executing random commands and things like that. All right. And so, just like we had for the first demo, we're going to have another useful tool to help us along with this demo. And this one's called ROP Gadget. And this is the de facto tool for constructing ROP chains. And how it works is it will automatically help us find the addresses of blocks of assembly code, or binaries, I guess, containing the instructions that we want. And the very basic usage of how this is going to work is we're just going to run ROP Gadget and then specify the file that we want as the binary, and then we'll use grep on the output. We'll pipe the output into a grep, which we can use to search for any specific command that we want to use. Some other useful flags that we're going to use, we have the depth flag, which will limit the size of the gadget's return. For example, if we do like depth 2, it's just going to look for that specific instruction followed by a return. But sometimes we're not always going to find the instructions we're looking for in just a convenient sequence of 2. So we might need to expand our search space to like depth 3 or maybe depth 4. And we'll go over what that'll affect when it comes to constructing our actual attack. And finally, a flag that will be helpful not for this demo, but for the additional one I've included, we have the multi-BR flag, which will allow you to return gadgets that have multiple branch instructions. For example, if you want to do a syscall and then return, a regular run of ROP gadget isn't going to give you any gadgets that contain both of those, right? It'll usually just give you a gadget that ends in a single jump or single branch instruction rather, because the idea is like you want to do this one thing and then redirect execution somewhere else, ideally to somewhere you can control. So if you want to be able to have a gadget that has multiple of these branch instructions, they have a special flag for that. All right, so let's get right into it. And we're going to be trying to use ROP Gadget to break into a simple admin login. So I'm going to go ahead and open back up this demo. Sorry, I should have included a picture of the situation here, but we're just going to go through it. All right, let's go ahead and go into challenge 1, admin pass. And let's see what this challenge looks like in code. All right, so we'll note that the setup of the buffer is essentially completely, or it's like the exact same as it was last time, right? So we have this buffer, and then we have this unsanitized input, but this time our goal isn't just to return to a function. This time you can see we have this target function, right? And what we want to do is we want to pass this check right here. We want to get past this authentication and get the program to print out this message of welcome admin. Okay, so fortunately, I mean, in this case, we know exactly what we need to do for here. So first we can see it's going to check if the isAdmin flag is 1, and then it's also going to compare the password that we feed it with the admin password stored right here, and then take in the password length to compare. And then it's going to make sure that the password we feed it is the same as the admin password, and then if not, right, the authentication is going to fail. Okay, so if we just think about the exploit that we're going to have to execute here, well, first we'll note that target isn't called anywhere in the code, so we're going to want to replace the return address with target at some point. But in order to get past this check, we'll note that we actually also need to set the arguments to target to the appropriate values. And if you recall, like we said earlier, we can use this ROP chaining exploit to set the register values to, the desired input. In this case, we're going to need to set RDI, the first argument, to the address of the password that we want to put in. We want to set RSI to the length of the password, and we want to set RDX to the value of 1 for isAdmin. So let's go ahead and jump right into it. And we're just going to start off by trying to go ahead and start using ROP Gadget. So let me go ahead and run my setup script. Here we go. Go ahead and clean this up, and we'll build our binary right off the bat. And now we're going to try to use ROP Gadget with a binary of, should be ROP Vuln from last time. And then we can grep this output directly. And we're going to start by looking for pop RDI, because remember, RDI stores the first argument that we're going to need. Oh, sorry. I think it should be ROP Gadget, or is it? It's lowercase ROP Gadget. Binary ROP Vuln. Okay, yeah, and that's going to run correctly. Sorry about that. And now we're going to put in the grep with our pop RDI. And then if you're going to run, we can see that it's actually going to give us a bunch of these sequences of assembly instructions that, well, they contain that pop instruction that we're looking for. And something you'll notice about all these sequences of instructions is they're all ending with a branch instruction. Like this is going to end with a jump. This one right here is ending in a return. This one's like a jump not equal, another jump. Yeah, most of them are jumps and returns. And if we get really lucky, we'll get a sequence like this, where we just have the instruction we're looking for immediately followed by a return. So let's go ahead and make note of this. I'm going to just write this down in our payload. and we'll work to construct this later. But let's go ahead and note that this is going to be the address of pop RDI ret, and this, we're going to note, is our first argument. Next, let's go ahead and look for a pop RSI so we can get that second argument in there. So same command, pop RSI in the grep. And yeah, we actually got really lucky again. We can see we have another sequence of just pop RSI and then return. And then I guess for convenience, I'm going to show you guys how to use the depth flag for this next one. So this one is going to be our second argument. And all right, finally, let's go ahead and look for pop RDX, but this time let's set a depth of 2 so we can just get a pop RDX and then the return that we're looking for. And we can see it actually didn't return anything, right? So unfortunately, we didn't get so lucky like we did last time. There's no sequence of 2 instructions that contains the pop RDX and then a return. So I'm first going to clean this up a bit. So we're going to have to try a depth a little bit higher than 2. Let's go ahead and try 3 maybe. Oh, and looks like we got pretty lucky. We got a pop RDX, pop RBX, and a return. All right, so let's go ahead and make use of this for now, and I'll be going over how we can, or how we're gonna have to use this a little bit differently soon. Okay, so actually these are just all the gadgets we need. We'll note that, well, it only takes 3 arguments, so we can go ahead and try to construct our payload now. So the idea, remember, what we're going to do on the stack, essentially what it's going to look like is we're going to have our padding, and because it's 16 bytes for the buffer, and then another 8 bytes for the saved RBP. And if we override the space for the buffer and then the saved RBP, that's going to put us right at that return address. And what's our first return address going to be? Well, it's going to be the first step in our ROP chain. We're going to tell the program, all right, here's step 1 of what you want to execute. So our first step is going to be to jump to this pop instruction, right? But how do we get the value that we want to get into that register using that pop instruction? Well, it's actually pretty simple and very convenient for us because all pop does is it takes the value from the top of the stack, pops it off, and puts it in the respective register that we passed in. So if you recall that what that first argument was, it's going to need to be the address of the password that we're looking for. And fortunately, we'll note that it's actually in the program already, so hopefully that'll be pretty easy for us to find. Let's go ahead and try to look for that now. I'm just going to mark this out. Next thing we're going to want on the stack is the address of admin password. I think it's just admin pass. And let's figure out what that's going to be. And to do this, let's just use GDB like we did for the last challenge. GDB ROP vuln. I'm not sure if this as admin pass will work here. We might need a different command here. Oh, okay, that is not password. Okay, I don't think this is quite right, so I think this might be an application for print, or maybe it's address of admin password. Yeah, okay, there we go. So this is an example of how you can use that print instruction I briefly touched upon earlier. So in the last challenge, we used the X command to directly read a location in memory. But if you want to instead read from a label, like the name of a variable, you can use the print command. And you can see here when we printed admin password, it gave us this Wells Fargo, which is what we're looking for. And right here, if you're familiar with C notation, the ampersand means I'm printing the address of admin password. So this is just going to give us the address of where admin password is stored in memory. And this is actually exactly what we're going to want because, I mean, in C, strings are just arrays of characters. And whenever we pass a string into a function, it's really just taking a pointer to the first character in that array. So what we're passing onto the stack here is the starting address of that string. So that's effectively what we're going to consider the address of the string itself. Hopefully that was sort of clear, but yeah, this is going to be the address of the string that we want. And this is Wells Fargo. Of course it is. Oh yeah, wait, I forgot I made like a bit of a scenario for this challenge. I think the idea was like Bank of America has this vulnerable endpoint that they've exposed, and you're trying to log in as an admin to, I don't know, I guess steal all their trade secrets, in the spirit of the Charlotte bank rivalry. I don't even know what I'm saying, but yeah, yeah, all right. Anyways, moving on from that, we can see that the next thing we're going to have to pass in is the length of the password that we're going to be using to compare between these two. Now, realistically, I think we could just put like 0 and it would always return true. But in this case, since we're passing in the exact password because we're just passing directly the address of admin password, let's go ahead and put the full length of Wells Fargo. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10. I don't know. Wait. Yeah, it's 10 because that's the null terminator. Okay, so we're going to want to pass in 10. So let's just say hex A. Length, string length. Okay, and then the last thing we're going to have to pass in is just this pop RDX, pop RBX return. So first, well, what value do we want in RDX? It's going to be our third parameter is admin. We want that to be a 1. So let's go ahead and put that into there. So we're going to want to put a 1 on the stack for is admin. But we'll note that this gadget, like I said, isn't as clean as our previous ones, right? So after we jump to this gadget, it's going to do our pop RDX. So we're going to get the 1 into RDX. But then it's also going to do pop RBX. So we can't just put the return address that we want to go to after this, because it'll treat whatever values on the stack next as, you know, the value it's looking for to pop into RBX. So we actually need to sub in some sort of garbage value to fill in there so that it'll have something to pop there. So let's just go ahead and put like, you know, garbage times 8. You know, let's we can do like the hex 41 like we did before. Okay. And so once we've done these three things, once we've filled in the values for those three registers, we're pretty much done with setting the permissions that we need to break into the admin permissions function. So once we've set all the parameters, we can just return directly to the target function, after which it'll perform the check and should hopefully pass because we filled in all of the parameters it's looking for. So let's go ahead and look for that. The address of, what is it, targets? This as target, and we're going to see it starts right here. Address of target. Okay, cool. So now that we've filled in the roadmap of what we want to do, hopefully this is making sense to you guys so far. If not, you should definitely go through and try using ROP Gadget for yourself. I've attached documentation just like I did for GDB, so you can read through that, learn about maybe other useful flags. I actually don't know too much about all of the flags. I just know like the depth and multi-BR because those are the ones I've used. But if you can find something useful, maybe you can do something cool with that. But let's just go ahead and start writing our exploit. So we're going to start by writing our typical garbage values, so just 24 of those to get us to the return address. And then we're going to want to write the address of that first gadget. And let's just pass that into here. And then we're going to use the same 2 bytes as last time, 2 bytes, 8, little. And now we want to pass in the RDI value. System.standardout.buffer.write. And once again, let's just do that same thing. Let's convert this also to 8 bytes. All right, great. And so after we run these, or after we put these 2 commands on the stack, it's going to jump to this gadget, going to pop this value into RDI, and now it's going to return, looking for the next address on the stack, which we're going to write out as this right here. So buffer.write this value, 2 bytes, 8, let's see, little again. System.standardout.buffer.write hex A, 2 bytes, once again, 8 little. And now we're going to write the next address. Sorry, this is a bit boring, like repetitive at least. But I promise it'll be satisfying once it works. And you'll be able to use this on maybe like a bit more interesting of an exploit in the additional practice exercise that I've included. But yeah, this should just serve as a pretty basic introduction to how the buffer or how the ROP chain is going to work. And we'll make sure to step through it as well in GDB once we're running with this input. So I'm going to be doing a lot of these 2 8 bytes right here. And then remember, we need to put the garbage right here. It's 41 times 8. And finally, we can now return to our target. It's going to be this, 2 bytes, 8, and little. So wait, how many memory entries are we going to be reading from RVP? So we have 1, 2, 3, 4, 5, 6, 7, 8 lines that should be getting written in. So just go ahead and build our payload. And let's enter GDB again. GDB, ROP Von, and we're going to set some breakpoints. We're going to set some breakpoints just like we did last time to sort of see what's going on before and after we enter our input. So we're going to actually let's just put a breakpoint right after we put in our input so we can see what's going on. Breakpoint right here, and let's run with payload.bin. And once again, we're going to use the X command. I think we should be writing 8 entries from here, so 8gx. Remember, this is just going to write 8 memory entries, display the values in hex. So x/8gx from just RVP plus 8, I believe. Okay, so let's go ahead and make sure this is looking right. Actually, this doesn't look quite right. What's going on here? 16 bytes. Let's put one in our RVP. So the RVP is going to have the frame pointer and then the return address. We get written. Oh, I didn't save the payload. That's why. Oops. All right. Sorry, this demo's a bit more scuffed. This is my first run through of it, but I don't know. Hopefully, it's good enough for video quality. Yeah. Leave a comment if you guys are enjoying this video, and make sure to like and subscribe. Yeah. Okay. GDB ROP Von. Once again, let's go ahead and set that breakpoint. Put it right here, and run with the payload. And this time, hopefully, we're going to see what we're looking for. Next, let 8gx RVP plus 8. And that does look a lot more promising. Okay, so let's take a look at what's going on at our start here. We can see we have our first, we're going to have our very first instruction right here, 40205F. And then we're going to have our value that we want to write to that RDI. And then we can see we have the address of the next gadget, and then the A value that we want to write, the address of the last gadget, and the 1, followed by our garbage values, and finally the last return address. And so to actually break up the instruction, or rather the execution of this a little bit more, let's try and see if we can, I don't know if I can actually read this instruction. Okay, I don't know what's going on here, but let's try and set a breakpoint. Oops. Okay. Let's try and see if we can set a breakpoint at this address plus 1. Does that work? No. Okay. Maybe it's this. Okay, yeah. So that worked. Okay, so basically what I just did is I set a breakpoint at the gadget that we just put in plus 1. So it's going to be at the return address. So hopefully what we see is that the value that we're putting in for the address of the admin password is getting written into RDI. So let's continue running. Okay, and now let's go ahead and I think it should just be print RDI or X, maybe we do like X1GX. And yeah, I think, yeah, this is actually exactly what we're looking for. We had the hex 499040 admin password has been written to that RDI. Great. So looking good. Let's go ahead and keep going down the chain. Let's copy this address right here, set a breakpoint at this plus 1. And let's go ahead and continue. This time we're going to want to see what's going on in our RSI. Yeah, and we can see it's going to be hex A, the A value that we're going to put in there, just the value of 10 for the length of the string. Next, let's go ahead and check in on that last gadget right there, this one right here. Well, the return is going to be at 2, but it shouldn't matter either way, but let's just put 2. And finally continue again, x/1gx rdx. And we can see that, yeah, that's just a 1 for the isAdmin flag that we're looking for. And now if we continue again, we should be going to target next. So let's just go ahead and put a breakpoint at the target function and continue. And so we just hit it, and we can see now looks like we might have a bit of an issue here. Let's go ahead. Yeah, okay. Looks like it worked fine, I guess. But yeah, it printed welcome admin, and yeah, we can see that it verified the credentials that we put in. Okay, I'm not really sure what's going on with this. Let me set another breakpoint at this point in the file. Breakpoints. Actually, let me just exit first. Exits, GDB, ROP Vaughn, breakpoints at there. Put in an extra asterisk. And let's go ahead and run with our payload.bin. And let's print the RDI value, or x1gx RDI. Yeah, that's going to be the admin password, x1gx RSI, it's going to be A. And finally, let's do RDX as well. It's just going to be 1. All right, cool. So we can see it actually has all the values that we're looking for, and it should be running correctly. Frankly, I'm not really sure why it's running like this, but I mean, clearly we have the correct values in the registers. So yeah, like I said, if we continue, you can see that we actually passed the check. It says welcome admin, and yeah, we've succeeded in completing our very first ROP chaining exploit. Sorry, that was a little bit scuffed. This is my first run through for this video, but yeah, hopefully that was pretty cool. But anyways, now to talk about the relevance in the real world. The ROP chain that we just studied isn't quite applicable in the real world. There are a lot of protections that I actually had to disable for this exercise, things like ASLR, which is address space layout randomization, and PIE. I don't really remember what this is. I think it's like processor independent execution or something like that. But the idea is it randomizes the starting addresses of the binaries in memory. And so these randomization matchers are pretty much just implemented to obscure the address space so that we can't find fixed addresses for the gadgets that we're looking for. And another common prevention for these ROP chain attacks, and Stack Overflow, or sorry, not Stack Overflow, another common protection for buffer overflow attacks in general is something called a stack canary. And this is just a value that you're going to put typically right between the saved frame pointer and the return address, and it's just going to be some fixed value that you obfuscate, and if that value changes, you know that someone's trying to override the stack and you don't let them execute whatever is coming next. So yeah, it's called a canary, right, because miners used to take their canaries into mines, and then like once they stopped chirping, they knew there was like noxious gases or something. I don't really know, but basically it's just a signal that something bad is happening, right? But even with these measures, there are ways to get around them. So these ideas of ASLR and PIE and stack canaries, they're all based on some randomization or random value that's unknown to an attacker. But if the attacker has some way to figure out what those values might be, then they can essentially negate all effects of these protections. If you want to learn more about an example of how they might figure that out, you can look into the Heartbleed attack. It was used for a lot more things than just trying to conduct these buffer overflow attacks. Maybe more significant is things like finding RSA keys, things like that. But yeah, the point is there are still ways to get around these protections, and it really just feeds into that whole idea of buffer overflows being really like a cat and mouse game of attackers and defenders trying to come up with new attacks, come up with new defenses against those attacks, and just in a constant cycle of, I guess, innovation and breaking the C language. But yeah, anyways, thank you guys for listening to this video and hopefully to my previous one. And like I was talking about earlier, I do have a third challenge for anyone who found this interesting and wants to try a little bit more. It's going to be this challenge 2, privilege escalation. And how this works is The challenge I have for this is we have this shell that's exposed to users. I guess in this scenario, you could imagine some company is providing a service that allows its users to execute commands in some shell under their like allotted permissions, right? And your goal is to try and use that ROP chaining exploit that we just learned about to exploit this shell command that they've given you and try to make it run as root. So you can gain access to a root shell and you just do literally whatever you want, right? So this is going to be an example of a privilege escalation attack, and privilege escalation comes up a lot as a common like attack vector or things that attackers will do once they gain access into a system. So hopefully this is an interesting challenge for you guys. If you found the other ones interesting, this will this will present a little bit more of an involved demonstration of the capabilities of ROP chaining, and you will need to understand how x86 syscalls work a little bit. But I've included documentation on that. And just a side note, just make sure you read the notes I've included, because there are some things about this attack that make it a little bit different from the other ones. So yeah, hopefully you guys have enjoyed this talk and the previous video. If you watched my talk at this point, hopefully you enjoyed that. And yeah, I hope you guys learned a lot and have fun.